All right. So yeah. So this part we discussed earlier that depending on need we can use it. For example, if we are making a phone book application, we want to store names and contact list, or name and contact information, as well as we want to store address information, we can use dictionaries. So it's a great data structure. One thing is important, and it is a must in Python, that the key is always a string. You cannot use integers. For example, you cannot put number 1, 2, 3. You cannot use like that. So you cannot put some numbers here. You really need to put some kind of string, for example, name here, age, any kind of keywords which contains number of characters. So hobbies, you can put hobbies, and then in hobbies you can put a list of hobbies, because one person may have more hobbies, right? So this is all available in Python. So if we see this part, there is nothing. Dictionary is empty. Here we see one key value pair. Here we see two key value pair. So it means dictionary has two entries. One is like name and age, and corresponding appropriate values filled as well, 10 and 67. And then we may have another entry like this where we have a key, again string. So we need to put some kind of characters here, which is hobbies, and a list of hobbies. So a list of hobby is itself a list, but we can put it inside dictionary because we are making a list of a person hobbies. So all such information we can put inside dictionary data structure. And then yeah, we were right here that we can iterate over dictionary just like we do over arrays, we do over list, we do over hash map. By the way, we didn't work on hash map. We worked for stacks and queues. So we can do iterations on all the data structures. And definitely we can search a value whenever we have data. Sometimes we need to search a particular value. So searching is also available in every data structure. But we will talk about majorly about the complexity, which means whenever I will say complexity, majorly I will talk about time complexity. So which means how much time a particular method or a particular algorithm is going to take. Okay, so we will discuss time complexity for searching, for finding an item in the data structure. We will discuss it. Yeah, so creating functions, all the basic stuff. How can we create a function with def? We give some, okay, some name, some parameters, and then we define it. Recursive function. So this is an important thing. I believe we discussed on that part. Somehow, okay, so it is a good thing to discuss today, because we discussed that, but not that much, because because of the length of the course, there were a lot of things to discuss. So let's talk about recursion. So recursion or recursive function is something which repeats itself. Unlike a loop repeats a task multiple times, but recursive functions are kind of repetitions of a function call, which means if I make a function recursive, do I have some recursive function? This is not recursive. How to convert an iterative algorithm to a recursive function? Yeah, so they have an algorithm right here. What it is doing, it is taking a lower number and upper number, and it outputs the number from whatever the range is. For example, I say from 1 to 10, okay? But it starts from 1 and it goes to 10, this particular loop, and then it prints every value. Every time I increment my, lower number so that I go to the next number, I can go to the next. So this is not recursive. So whenever we talk about recursion, which is really important because recursion is very much useful in advanced level of applications where your code is kind of really in need of repeating some task over and over again, and you have to make recursive function. So let me show you the basic difference. So when either we write the code or methods which are iterative or recursive. So whatever we were doing so far was iterative, which means your method may or may have some kind of, uh, loops. Okay, it may have loop or maybe sometimes it doesn't have any loop, but that code is not recursive. So such loops are called iterative. Okay. If you are using recursion means a function or a method, whatever you say, a function calls itself. This is recursion. For example, I have a sum function, and this function has some lines of code right here, and then it also calls itself like this. So this is a recursion function. Okay. So now, either iterative or recursive, whenever we talk about solutions of certain problems, so they are designed either as iterative solutions or recursive solution. Iterative means no recursion. Recursive means a function is calling itself. This is recursion. Okay, so they have a good example of repeating a task where they are printing some numbers, right? This is, they have a loop here. It is repeating itself, but there is no method call. No, we are not calling display range inside display range. So this is not recursive. This is one, quick hint to see if this method is recursive or not. So if a method is recursive, this name should appear somewhere inside this code, which is not there. Okay, so it is a simple method which is iterative. It is printing some numbers. Now, let's see. Yeah, right here. Right here, they have another definition, equivalent definition, which is doing the same thing. However, the code is different. This time it is recursive. Recursive means the method is calling itself again and again, So what they are doing, this is important to know. Display range, it is taking again lower and upper, and we don't have a loop here because now we don't need a loop. Our method will call itself. So that will be the loop itself, because here inside a method, I am calling my method again, which means with some different numbers, lower plus 1, which means this function will be called again. Then it will come here, it will print a number, this function will be called again, and so on and so forth. So this method will repeat itself so many times. So instead of the loop repetition, we have a method which is going to call itself, and the method will be, executed again and again. So this is recursion. The equivalent recursive function performs similar primitive operations, but the loop is replaced with an if statement. So I have no idea if you have ever worked for recursive function. If you can, just give me a quick input on that. It will be helpful because I plan to do some kind of, examples on this topic, maybe 1 or 2 today, before proceeding towards complexity part.
Yeah, I feel like we could use more work on that.
All right.
Or I could.
So yeah, so this is a little bit of advanced whenever we are good in, writing basic functions, which means iterative functions. So then we can write recursive functions as well. Starting with, starting directly with recursive function doesn't make sense. So I think we spent plenty of time on writing different methods in the code. writing classes. So now it is a good time that we can, make some examples for the recursion and see how good it is, why we actually need it. So starting from the same example, just to show you that how a recursive function, executes using, debugging part. I want to show that part. So for example, let's implement the same, same recursive method here instead of, writing anything else. So if I design this example right here, display range. And this recursion is very, very powerful concept in programming. Some tasks, some algorithms, some problems are just not solvable without using, if we don't use recursion. So that's why this concept is really important. In this example, we have solution, which is good, which is not very bad. We need recursion when our solutions are either going, they are taking so much time, or we need recursion whenever, our code is getting so much messy and we are repeating certain parts. So it means we should use recursion so that code is really concise and, it repeats itself instead of we repeat it. So if lower less than upper, we are going to print the number and then, okay. Okay, let's do that. So then I will call the function again with lower +1, because this time I want to print, but I want to print the next number. So next number will be lower +1. However, this method takes 2 parameters, so I have to pass 2. So this is kind of, it looks strange, but it is really, it does the trick. And let's see how it works. Let's save the file. I'm going to save it somewhere. No, not here. Maybe on desktop. Korean one. Okay. So let's debug it. Let's see what happens. First of all, see the output. I haven't called it, so I should call it. So display range, send some parameters, for example, 1 to 10. So it should print 1 to 10 numbers like this. So it is printing 1 to 10 numbers without using loop. Instead of it is using, it is using recursion for repeating. Okay, let's see how it works. I am calling the function 1 time, but it is somehow printing 10 times. However, I don't have a loop here. So this is recursion. In other case, if I provide that iterative definition, it should be like this: lower, upper. That makes it really very clear that we have a loop here, for loop, while loop, whatever. You can run, whatever you want. Less than equal to upper, and then print and increment. Okay, increment lower. Okay, exactly same definition. Here, anyone can see, and if you know the code and you have idea of programming, you will quickly see and tell, okay, this loop is running as many times depending on the range. So you are giving a range and the loop is running range number of times, okay? And then you print that. So it looks really straightforward. But here it is not like that. It is not that straightforward. Let me see if it is running that code. Yeah, so it is running it still. There is no confusion for it. Let me just put a breakpoint. I believe it is running this part because I have 2 methods with same name. So let's see. Let's start debugging and see how it goes. Control F5 or F5. Oh, no. F5, yeah. Okay, so it is running the recursive function. So here is the method call. So after that, it goes up right here and it is running this code. So leave this code here. It is not affecting anything, right? Because I really want to see how this code works. Okay, so we are right there on the same point. So let's debug step. Let me just see the keys. So step over is F10, step into is F11. Okay, so step over. Oh, really? No, I need to do step into. Start debugging. Step into F11. Okay, so we need to press F11. What is happening? I did F11. Why it is not? Okay, let's see F11 and then what happens. Now the method is being called. F11. Yeah, we are there. Okay. So this method is being called with number 1 in lower and number 10 in upper. We can see that right here as well in the left pane. So now it will compare. So you can use the same key step over, which is F10. F10, it is going to print single number lower, which is 1. So it has printed 1 down there on screen. Now we need to, run it again. So what we are doing, we don't have a loop. Instead, we are calling the method again with a different number. Now my number is lower plus 1, which means my number will become 2. Earlier it was 1. Now it will become 2. And the method will be called again with number 2. Upper will be same. Upper is 10. So 2 and 10. So it will take 2 and 10 and it will call the method with, different values. Let's see. Step into F11. Yeah, there. See, lower is 2. Because we passed 2 from here, a different number from here. Now it is checking if 2 is less than equal to 10. Yes, it is. It will print 2. Then it will call for 2 plus 1, which is 3. So in this case, it will keep on repeating. Oh, I press F10. I came out of the out of the method. So basically in this case, in this way, it will keep on repeating 10 times, and then it will print all the numbers one by one. Every time we are here, we print one single number, and then we call the method again. So we go here, and then we run it again until make sure your recursion runs on the base condition. So this is your base condition of the loop of your method, which means if this condition is not correct, this method will keep on calling, forever. So your base condition tells when to stop. So we are really, concerned whenever we are writing a recursive function. So your base condition should be met. Otherwise, loop, it will be infinite thing. Okay. Thank you. So I just saw the message. Okay. So yeah. So base condition should be met so that this particular recursion stops at a point. So if lower is less than equal to upper, so this is our base condition. So I'm making sure that this is, kind of stopping, right? So this example makes sure how it keeps on increasing lower plus 1 every time I call the method. So at some point, this lower plus 1 will be, it will become higher than upper. So the loop will, stop. This recursion will stop, okay? So this is my base condition right here in the code. So every recursive code has a base condition so that we can stop at, on that. So this is one example. Now there are many. For example, I believe we worked on the factorial example. I'm not sure really that we discussed that factorial one. Let me just stop this part. Okay, this is already stopped. No, okay. So you have seen how recursion works, okay? So Yeah. So there is one example I discussed earlier as well for Tower of Hanoi. Let's discuss that part. I share you guys with some kind of link which was, for the visualization, right? Let me just open up. I believe they have some kind of Tower of Hanoi example as well. Let me just open up. Because this is really big example, Tower of Hanoi for recursion. Yeah, right here. Oh, good, cool. So this is Tower of Hanoi. The idea is let me just put something here. Number of disk. Okay, so it has number of disk, and algorithm should work in the way that a bigger, you should have a bigger disk down, and smaller disk should come on top. That's the idea. For example, I have 10 number of disk, new input must be an integer. Okay, they can, okay, because 10 will be very big. So let's put 3. That's better. New. So you will see, oh, that so speedy. Stop. Okay, so I have put 3. So you see 3 disk here. Okay, it should, work in the way you have, this is implemented using stacks. This is a stack. This one is a stack. This is a stack, which is holding the disk somehow, over it. So let's see how it works. At any point, we cannot put a bigger disk on smaller. Let's see what happens. First of all, it should. Okay, the last one. Okay, so what they did, they moved the disk from one stack to another. This was the goal, that you have to move the disk into, another stack. And at any point, you cannot put a bigger disk on a smaller disk. This is the basic, requirement for Tower of Hanoi. So earlier they had 3 disks right here. Can I do it again? I believe I should. No, I don't know. How can I restart it? Okay. It was very fast. Slow down. 7 total moves made. So it is telling how many moves made. And see here, the code is this. And this code is based on recursion. So your main method which solves, I mean, there should be more lines as well, but the basic, code for implementing it is based on the, calling a method itself. So this is your method solve. It calls itself. Here, it calls itself right here. So this implementation is based on, recursion. Can I? Yeah. So let's do it for 4. Spindle. Okay. So it is putting 4 disk, and the plan is to move that, to the other stack in the same way. Yeah, solve. The middle one is spare extra. We are using that stack so that we cannot put bigger disk on smaller one, because this is the rule of Tower of Hanoi. You cannot put bigger disk on smaller one, and you have to arrange them and move them to the other. Now the bigger will go on the actual goal. And now, okay. And now smaller will go again in the middle. Yeah. Oh, yeah, there, okay. Okay. So this is Tower of Hanoi, which is implemented using, using recursion. Without recursion, if you try to solve it, it will be, I mean, it will take a lot of time, and then ultimately your code will be kind of really, repeat based on repetitions. So using, recursion, it is that much of the code. Rest of the thing is just the method call. How you're calling the method again and again with different number of disks here. Yeah, so this is really, the actual use where we really need to use recursion. This is one example. There are many in mathematics. There are, a lot of examples where we use, recursion, and without recursion, we cannot work with the, we cannot actually solve the problem. So let's talk about time complexity. We have to work on time complexity from chapter 2, right? So let me just grab the book. Yeah, we discussed that. So they have another example where the method is calling itself here. Okay, so in this, I mean, this is again a recursive function. All right, so recursive function calls itself. Whenever a function calls itself, so it is recursion. Okay, then they have, I think, without recursion solution as well. You see, here we don't, oh no, what we have. Oh no, it is also recursive. So they are calling the method itself. So I mean, it is good that they have good examples on the screen, and then they print this, kind of output on the screen using recursion, which is cool example. Okay, another. So they have Factorial. Wow, good. So let's discuss this example. This is really good. Factorial means, yeah, multiplying a number with itself until we reach to, 1. For example, 5 factorial means, where I am here, 5 factorial in mathematics should be 5 times 4 times 3 times 2 times 1. I can write the code in using iteration where it will be a single loop which will run until I go to 1, and I will keep multiplying the result. This is one solution. Okay. The other solution is if we write the code in a way the book has written, which is recursion, where we will start from the basic number, which is 5, but then we will call the method again using recursion with the 1 minus number until we reach to 1. So a function will keep on calling itself with -1. First time it will call it, 5 for 5, then 4, then 3, then 2, and 1. And, finally, when all function calls are done, numbers will be multiplied. This is recursion. And okay, we can see it right here. First of all, let's see the loop. Where is the loop? They don't have it. Okay, no problem. This is recursive definition. Let's see. So I told you that every recursive function should have a base condition, which is the stopping criteria. So let's discuss this definition. Factorial. We are computing factorial of a number n. Okay. Okay. This is good. I mean, there will be many type of codes you will see. You can even write your own code. This parameter is not a must. If I write it, I don't use it, but it's okay because they are using it. So product means they are putting all the results in this second, product variable, putting all the values there, which is okay. So n is the number for which we are going to compute factorial. So the base condition is if n is 1, return the result. It means we have done all kind of multiplications because we have done minus, minus, minus until we reach to 1. So when number is 1, return whatever the product is. Before that, keep returning factorial with n minus 1, which means if number n is 5, so call it with 4, 3, 2, and 1. And also keep storing the product. So they are storing the product here, n times product. product is, a basic variable which is having 1. We cannot put 0 here because otherwise multiplication will be 0. So they are putting 1 here. So product will store the product of all the numbers. So here they are doing n times product. So if you return it, which means this product will be, containing all the values. So this method is calling itself again and again. Okay. So let's go to the part map and filter that was already done in the, in the assignment and projects part. So I'm just not going to go over that. What I plan to do is second chapter. That is the important part. And before moving towards the book examples, where they have a lot of, it's not second, it is third. Okay, no problem. In second, they are talking majorly about collections. So collections can be sorted, unsorted, depending on the need. For example, we worked for bag, right? So bag is kind of, unsorted data. Anything can be there in any order, just like a set, right? So if set has 1, 2, 3, 4, or another set has 4, 3, 2, 1, both are same because order doesn't matter in set. So set is, example of unsorted collection. So there are many types. For example, all of these are collections. Graphical, graphs which is used for searching information. Trees, again used for searching. List for storing, different kind of data like we worked on. For example, queue, stack. Priority queue is kind of customized queue. For example, I have one queue for very high priority task, the other queue for very low priority task. So I can, make priority queues as well. Yeah, and then bag, dictionary, and set. I mean, all of these couple of collections we used, and every collection comes with the basic functionality. We can check the size, we can iterate over the collection, we can return the string representation. This is what we did a lot. We implemented these methods. Length, in, I'm not sure about in. At some point, in was there where we check if it is, if that item is inside that collection. So then we use this in operator. For loop is for iteration, string is for string, returning a string. Equality is used for checking if two collections are equal, and all of these operations are equal for every collection by default. Okay. I mean, we don't have to do anything. These are already available in object class. So whenever we write our own class, we customize the method according to our need. So this is what we did. And that's why we see underscore, because these are built-in methods. However, we provide our own definitions for our class. Okay. Yeah. I believe in this chapter, they just discuss about the major collections. Yeah. So now come to the complexity part where we want to see the complexity of algorithms, which means efficiency of algorithms. We are not talking much about the space complexity. Complexity can be either time or space. Whenever we are going for good time efficient algorithm, which takes less time, right? Time efficient algorithm means an algorithm which performs really well, which gives the result really quick. So when an algorithm is good in, is when an algorithm is good in, in terms of time, that algorithm will be compromising the space at some point. So there is always a trade-off between space and time. Okay, where is my board? So which means I can draw a line, something like that. I don't know. So this is my time, for example, 10 nanoseconds or milliseconds, whatever, 20 milliseconds for a program, for example. So it is increasing here. And so if my algorithm is, some algorithm is taking 20 seconds, 20 milliseconds or nanoseconds, whatever it is, this algorithm is taking 20 milliseconds, okay? This is time, how much algorithm is taking. And if I see that, okay, that is a big task, but algorithm is quickly working on that, it means it is efficient. If it is efficient in terms of space, if I put space here, this is space and this is time. This algorithm will be using more space in memory whenever it executes. Another algorithm which takes less time, same task, less time than algorithm A. So which means in terms of time, B is better because B is taking 10 seconds, 10 milliseconds. However, A is taking 20 milliseconds for doing the same task. If it is like taking less time, so make sure that space taken by this algorithm will be higher. It is taking less time. However, space taken by this algorithm will be more because it is running efficiently. So somehow it is using the space and doing something there. So there is always a trade-off. Okay. So it is not like that. If you are time efficient, so you are space efficient as well. No, it is opposite like this. Time increases, space decreases. Space increases, so it means time decreases. So there is a trade-off always. Okay. So now comes in today's world, I mean, if we are not working for, for trillions of records, right? If we are not working for such applications, then we really don't bother about that. We have good computers, we have good laptops, having, a lot of memory, a lot of storage, clouds, everything, right? So we really don't concern much about space while working for, for smaller applications. When we are working for bigger applications, bigger means when we are, using clouds, when we are in networking, our applications will be accessible for, millions, billions of people all over the world. Then it is really important how much space it is taking. Okay, how much time efficient it is. So otherwise, whenever we talk about a general algorithm, we are not concerned very much about space. We try to minimize time. Okay. So that's why whenever we talk about complexity, so time complexity is the major thing we talk about. Okay, all right. So now let's talk about the time complexity, what it is that. There are certain, criteria. How can we measure the efficiency of algorithm? Again, about time. How efficient is an algorithm is performing. So, I mean, there are many processes. However, the best one is one which includes mathematics and whatever we say, big O of notations. We will talk about it later. Before that, we will discuss what else can be possible. If we don't want to go into that mathematics part, what else is the possibility? So we will talk a little bit on that, and then we will proceed towards the actual useful applicable way which is used by theoretical computer science as well as practical algorithms both to measure the time efficiency of an algorithm. Okay, so it is a step-by-step process. So we will cover this part after the break. All right, this is the focus. After that we will see if we can do a couple of coding examples. That's the plan for today. Other than that, we have covered stacks. And that was all about this course. We will be covering more in B part of Python. So let's take a 10 minutes break and then we start working on this part for checking, measuring time complexity of an algorithm. All right. Yeah. Let me put a timer for 10 minutes and then see you guys in 10 minutes. All right. My same timer comes up. Resume. All right. So we were right on the point how to measure the complexity of an algorithm. So an idea is that maybe whatever algorithm we have written, whatever program we have written, what we can do, we can use, some built-in time method, which can actually check how much time this code is taking. So for example, they have written a code and then they are using start time and then end time, and then they print it. Okay, so first line they write whenever the loop starts, because loop is the major thing which takes time, right? Other operations are constant operations. Single line operations are constant time operations. Okay, so we say it like constant or like big O of 1, which means they take like really not much time. They are just constant, some number. Okay, but whenever loop comes, we have to measure how much time that task is going to take now. So they measure the times in start and then they subtract start time with end time and then they print it to see how much time this code is taking. And in this code, they have one loop and then they have another loop inside. So two loops inside. One loop is inside of another loop, okay? And they print some numbers here. So problem size in seconds. Now what is it? So second means how much seconds a particular problem is taking. And then there is size. So size means if problem size is this number, okay? A particular number they set. For this particular number, the time took by the program is 3.8 seconds. Where they are changing it, let me just see problem size. Oh yeah, so right here they are using a loop which runs problem size number of times. So if your problem size is 10, so the loop will run 10 times. If problem size is a million, the loop will run million times, okay? So that's why they are talking about problem size. If problem size is a particular number, they compute what is the time, because your loop is based on problem size here, right here. Outer loop is going to run 5 times. We know that. But inner loop is based on problem size. So when they compute, they see these numbers here in the figure. So it is telling that, okay, if your numbers are, this, it is like 3.8. When you double it, kind of 2 times the previous problem size. I see this number is also doubled, right? Yeah, this is also doubled, almost. Then they make it like, again, they double the previous one. So 2 times 2 is 4. So they see 7 times 2 is 14. So this number is also getting doubled. Almost, not exactly, okay? If they do it another double, like 4, there was a 4 number, now they are doing 8. The problem size is 8 and number of zeros is the same. So here the times taken by, this problem size 4, it is 15. For 8, it is 30. So almost a double. So let's see what they talk about. A quick glance at the results says running time more or less doubles. Whenever the size of problem doubles, the time also gets doubled, right? This we can see in the picture. But in this solution, there is a problem. The problem is, I think at some point they discussed the problem here. Yeah, exactly, right here. 2 major problems in the technique. I mean, we can put this start time and end time in every program, whatever we are doing. We can write these lines on top and in the end and see what time it is taking. But does it really matter? What is the actual time it is taking for a particular input? No, because different hardware platforms have different speeds. One hardware or one operating system may be slower than the other. Okay. The performance of the system itself, your computer performance or your laptop, depends on the hardware, what kind of hardware you have. So depending on that, this output will differ. So if I see these numbers on my side, I mean, it is not a must that you will also see these numbers. Your number may be much better, or maybe, much worse than whatever we see here. Because everyone has a different hardware settings. And the system takes time, processing time of each system is different. So that's why running time of an algorithm differs from machine to machine, and that's why running time of a program will vary for different type of operating system as well. So it doesn't make sense if I compare my output with your output, because there are other parameters which counts, right? And then another important thing is software also depend on how fast is the algorithm. Different programming languages and compilers performance is different for each programming language and for each compiler. For example, they gave a very good example. C usually runs faster. That's why operating system assembly, the low-level code for the operating system is written in C because C is faster. If we compare C with other languages, for example, they are comparing it with Python. Algorithm is same, code is same, only the language is different. So the performance is different. So we cannot compute the time in this way by putting a start time and end time and then subtracting the times. Okay, this algorithm is taking this much time. No, because that time will be different on a different computer. That time will be different when you are using a different language. So you cannot generalize it. So we need something which everyone can generalize, everyone can use. Okay. Yeah, and then it is impractical to determine running time for some algorithm with very large data sets. Sure. For example, my algorithm, I am using an algorithm for trillion of records. It is picking data from different clouds, and then it has to work somehow over that and then print something. Okay. It is returning me some file by populating the data from trillion records. Okay, so maybe that task is going to take some hours, um, or maybe 1 day, or maybe 2 days, right? Depending on the task, whatever we are doing with the data. So does it really make sense that we are going to check the time by putting start time and end time for such a big, large data sets? It doesn't matter. It doesn't count. We cannot waste time just to, run the algorithm and see how much time this is taking. Okay. So these are the core points which motivate the, scientists and algorithms and developers that there should be some technique which should be generalized and which should not take that much of your time, right? Some days to count, to check how much time this algorithm is taking. I mean, crazy. Then there is a counting instructions part. So they discuss that counting instruction is another estimate. But again, okay, instructions that execute the same number of times. Yeah, instructions whose execution varies on the problem size. Okay, so whenever you count instructions, again, if you are using a different language, counting instructions will be different. Okay. So in general, counting instructions is also not a good idea. So this is what they are discussing right here. And I think they are counting the instructions as well here. Let's see. Okay, iterations. Yeah. So they are checking how many times if problem size is 1,000, how many times the code is running. Maybe it is taking these number of iterations. When I double the problem size, which is 2,000, it becomes 4 times. When I again doubles, which is 2 times 2 is 4, it again becomes 4 times. 4 times 4 is 16. So, I mean, they're giving an idea that, okay, we can do maybe like this by counting the instructions. So they are counting by doing like, adding the numbers plus equal to 1 every time a loop runs, they are adding 1, something like that. They are, using this strategy. But again, this strategy is not generalized. What a generalized solution is, let's talk about that. That is our complexity analysis. This is the mathematical solution. And the good thing is we really don't have to go into the exact mathematics, how it is derived. We should know the basic terminologies and we are good to go. And this is really good thing about complexity analysis. Yes, it matters. It will take time whenever you are making your own algorithms, for which you really need to you really have to do the analysis. And basically this kind of complexity analysis is done in theoretical computer science. In practical computer science, like in software engineering or data science application, wherever you are using algorithms or writing code, you should know the basic terminologies, and then you should know how to apply these terminologies how to quickly check efficiency of an algorithm. And this is what we are going to discuss, okay? Because this is what we really need. We don't bother of how this terminology came, what is the actual mathematics on the back end, what about these notations, what are the actual proofs for the notations. We don't care. We know that this is the criteria and we will apply it. That's it. So let's see. You develop a method of determining the efficiency of algorithm. Again, it is time efficiency, not space efficiency. Determining the efficiency of algorithms that allows you to rate them independently of platform dependent timings or practical instructions counts, right? Yeah, so this is called complexity and analysis. Entails reading the algorithm and using a pencil and paper to work out some simple algebra. Yeah, really simple, very basic. So let's talk about orders of complexity. That's a core part of it while we are while we want to do complexity analysis. So for example, we have two counting loops. Yeah, same loops we discussed earlier. First loop executes n number of times, n may be 100 or I don't know, 1,000 or maybe a bigger. For a problem of size n, okay. So the first loop is running for the problem size. So if problem size is n, so it means loop will run n times, right? The second loop contains a nested loop, okay, that iterates n square times. The amount of work done by these algorithms is similar for small values of n, but is very different for large values of n, okay? This is problem size. When I say problem size, let's clear that idea. Sometimes people get confused. I mean, when I was new, I was also like kind of, okay, what is problem size? What is n? A couple of terminologies, but they are actually saying one thing. So let's discuss that. So whenever I say problem size, whenever I say n, whenever I say, data size, or whenever I say, array length, all of these terminologies are basically representing same thing. Array length is kind of very specific according to the coding that we have an array which has length of n, which means n elements. Whenever you have n elements, you have to iterate through the elements. So we talk about n. N is the general number. Problem size is again same thing. Data size is same thing. How? Because all of these terminologies are referring to a loop which runs n number of times. So when problem size is 10, loop will run 10 times. Problem size is 1,000, loop will run 1,000 times. When problem size is million, loop will run million times. So this is your problem size. So iteration totally depend over it. So what they are saying right here, they say for smaller numbers, it's okay. For smaller number, when problem size gets bigger, of course, operations, it takes more time. Work is, kind of more. But when problem size becomes square, which is n square, for example, double, right? You had 10, now you have 10 times 10, which is 100. So when you are kind of, the amount of work done by algorithm is similar for small values of n, but it is very different for large value of n. When n will be bigger, for example, a million, let's forget about n square. We will talk about n square later. Keep it n. If it is 1000, it's okay. If it is 10,000, it's okay. If it goes to million, trillion, then it's a problem, because then that problem size or that number n will actually affect the time. This is what they are saying here. That n keeps on growing, growing, growing. When it becomes, it goes to a level which is a big, then it is going to affect your time, your algorithm efficiency. It will show. Currently, I make a factorial or factorial program which computes factorial of a number which is 100. Then I make a number, then I run it for 1000. Then I run it for 10,000. So once you make the number, big, after making it, taking it to a certain level, time, your program will, will take much time, will start taking more time. For example, right here, I was computing factorial, do I have, no, I don't have it here. Okay. For example, I set this upper bound really very big. Okay. So, definitely if I make the number like this, okay, so this is a problem. Okay, all right, it needs more memory. Okay, let's delete this recursion, because okay, with recursion, let me just see. Okay, 994 more times. Maximum recursion depth. You see, when you make your function call again, it goes to memory. So when I'm calling it this number of times, your memory is getting full, your random access memory, because every function call goes to your memory. So now they are not running the program. Okay, that's fine. So that's why I'm going to delete this recursion, because recursion makes your stack full. Your random access memory has a part where this program loads. So that stack is full. So let's do it other way. It is running, and now it will take time, right? Because my number is, you can see the number. So this is what I'm talking about. Once you make the number smaller, it's okay. But at some point when numbers go to a certain level and they're big, then they are going to affect the performance. And at that time, we talk about time complexity. For smaller numbers, we really don't care, right? Let's make it stop. That's enough. Okay. So yeah, so let's talk about more. Yeah, this is what I was looking for. So let's see the terminologies for complexity. But we need to know how to check the complexity of algorithm. So this is a cool paragraph over it. Let's do it together. I mean, it will actually make your concepts clear. The performance of algorithms differ by an order of complexity, right? Order can be linear, order can be, square, order can be quadratic, right? Like quadratic is here. Quad means 4, right? So order can be linear means, it's n. Let's talk about mathematics, because we need to learn a little bit of, maths to understand this concept. When I say linear, oh, where is that? So linear means n is a linear function, and n is a number. I mean, it is not a function, but n is linear. When I say quadratic, so it means I am talking about n, an exponent, for example, 4. I am raising the number with some particular power. So definitely when my problem size will be n, and performance of an algorithm, which is going to run n times, will be different if I compare it to some algorithm which is running n, n raised to power 4. Because n raised to power 4 is a bigger number than n. So this is linear and quadratic terms. Let me show you again to the book. The performance of the first algorithm is linear in that it grows in direct proportion to the size of problem. So linear means you have a loop and loop runs n number of times. This is linear. If you change your n, which is 10, loop will run 10 times. If you change n to 20, loop will run 20 times. If you change your loop to 30, it will run 30 times. This is linear. This function is linear, the loop is linear, the algorithm is linear. However, the behavior of second algorithm is quadratic in that it grows as a function of square of the problem of size. Okay, they're talking about the square. Sorry, that was my mistake. I'm on, I don't know, where is my mind? Okay, so quadratic, they're actually talking about square, right? Because quadratic formula takes square. Okay, so let's go back to that. So let me put it 2 here. So they are talking about it. N raised to power 2. It's a bigger number, sure, if I compare it with n. So they are saying that problem size is n. And if algorithm is taking n square, how it is taking, we will talk about it. But they are just talking about it, giving it as an example. If an algorithm is taking like, quadratic, it is like more than linear. And how the second algorithm is taking quadratic, let me show you. That's the point where we come and see how the code is working, what the time this particular code is taking. Let's see. Let me show you. We have discussed plenty of the material, so now we should be good to go. Where is the algorithm number? I myself, okay. Figure 3.3. I mean, they are talking about we have 2 loops here. This is also n square. I really want to make sure which examples they are talking about. The output, order of complexity, the amount of work in the, okay, they are talking about the tester programs. So they have 3 tester programs, and they say work for the first algorithm grows like this. When problem size is 2, efficiency is 2. These are some numbers, okay? Assume efficiency is 2. Problem size is 10, efficiency is 10. Problem size is 1000, efficiency is 1000. Now, how they are computing this efficiency? We talk about it from the example. But I can tell you from this part, from work of the first algorithm and problem size, that this is a linear algorithm, because as problem size grows, the time or the work of algorithm grows according to that. And I can also say that this algorithm, whatever the algorithm is, it has only single loop. Because if your loop is single, only then it can be like this in a linear form. So they are mainly talking about the algorithm which we talked on top. Of course, not this. Output tester program. This is a tester program. Where is the first tester program? This one, yeah. This is second tester and this is first tester. They are talking about it. Really? They have 2 loops here. Prints the running time that doubles using a single loop. They have this loop which is running 5 times. Yeah, okay. So basically, they are not counting this loop. Make sure, so this is called constant. Whenever you have a particular number set, another important thing is constant time. Linear, quadratic, and constant. Let's talk about it. This is really important to measure time complexity. So we are in the concept of measuring time complexity of an algorithm. Okay, how much time an algorithm takes. Linear, quadratic, and constant. Constant means whenever you have a number, specific number. For example, a loop is running 5 times or maybe 100 times. We don't bother about that. No. However, if this 100 becomes like million, then we bother about it, but it doesn't happen like this. Okay, your code will not contain a number like this. So normally such numbers are really small. So these numbers are counted as constant time operations. So any variable assignment, for example, I'm putting time equals 10. This is constant time because I don't have a loop here, which is depending on a number. I don't have a loop. So every instruction takes constant time. Okay, if we don't have a loop, only then. So basically in this example, we have a loop which runs 5 times. This is constant. We are not talking about it because we know this will run 5 times. This is a particular number. Forget about that. However, when I come inside, I say for X in range problem size, and problem size is really big. And it will be more bigger. OK, so for first time, they are using this number. So this loop is going to run according to whatever problem size is given. OK, so consider outer loop is not there because that is going to run only 5 times. However, the other loop is running a lot of times. So we are talking about that loop. And time complexity will be computed using that. Rest of the operations are constant. So constant means single operation. Constant operation, constant operation, constant, constant, constant. We talk about this loop. Rest of the operations are constant. Very simple. So mainly we see the loops, how many loops you have in your code. Then, because this loop is totally dependent on the problem size, so this will tell us the time complexity. So our time complexity is in the worst case. In the worst case, this loop is going to run for a problem size number of time. So if we have this, this size, which is really big, so our this loop is going to run whatever, problem size we have set here. OK, so this will help us in computing the time complexity. So let's see how to compute time complexity for that. Let me show you. We have discussed that this loop is going to run problem size according to the problem size we have here. OK, so here we have this loop, which is going to run, specific number of times. And this will tell the time complexity. So whenever we talk about time complexity, we have seen a loop. All of the operations are, in the example are constant. So we don't bother about that. We have a for loop, which runs, according to the problem size. So this will matter for computing the time complexity. Now, for computing time complexity, either we talk about worst case, and mainly we talk about worst case. Worst case complexity means what is the worst possible time this algorithm will take in the worst possible situation. Best case occurs the minimum possible time. Average case means on average, just like we talk about average. So on average, including worst cases, best cases, regular cases, what is the average time this algorithm may take? So we talk about mainly, worst case. However, sometimes we talk about best case and average case as well in algorithms. But mainly we should be concerned that this algorithm cannot go beyond this time. That's the worst it will take. It can achieve better, it can perform better, but in worst case, it is going to perform like this. Now, let me give you example. I am saying our complexity depends on the loop, and loop depends on what is our problem size. So if this loop runs n number of times, which means if n is 100, which means problem size is 100, this loop is going to run 100 times. For example, my algorithm is find a number in array. This is my, this is my code. Algorithm is written for finding a number in the array or in a list. So this is my list. I mean, list may have any number of elements. For example, here I'm saying 100. So 100 elements here, and first element I say is 1, 2, 3, and up to whatever. I am going to search 1. Now my algorithm for finding a number, I have an algorithm, I am checking complexity of an algorithm who has a name, find a number. This is my code. or algorithm, which finds whatever number I give to that. I have a couple of lines here, how this code works, and I'm going to check the time complexity of this method. Find a number. So suppose I give it a number which occurs right here, right on the first item, right on the first location. Okay, this is the best case. Whatever you are finding is, is residing on the first, in the first element. Your algorithm will find the element and stop. This is called best case. Worst case is I have to, find everywhere. Finally, I found it in the end, right here. This is the worst case. So we compute complexity mainly for worst. Okay, it is going to run maximum n number of times, 100 number of times, and it will find the element. That's the idea. And this notation, big O, is used for worst case. There are different notation for average case. For average case, we have something like this. If I really, no, I don't know from this book, but let me just check and verify. For average case, we have this notation, a round sign and a minus. For best case, we have omega like this. I mean, people name it differently, but this is the sign, big omega. Okay, big O, big omega, or big theta. This is the theta. The lower one is theta. This is like a theta, yeah. Big O and a minus. Yeah. So these notations are used for, for marking what is the worst, what is the best, what is the average. These are used in theoretical computer science. We mainly talked about a big O, which is the worst, which means your element was in the end. You were finding an element in a list and it occurred in the end. So we compute time complexity, which is the worst, so that whenever someone says, okay, my list has 1,000 elements, I will say, okay, this algorithm will not go beyond big O of 1,000. It means your code will run 1,000 times and it will find the element. It doesn't have to run 2,000 or 10,000 times. Okay. So that's why we use this notation, big O for worst case, and then we put n here, which is problem size. The rest of the operations are constant time operations. Now, back here. So this code is going to take big O of n, because this loop is totally dependent on problem size. But then they have another loop, another tester program. Right here. Yeah, this loop. See, first loop runs problem size, and inner loop runs again problem times. In this case, your complexity will grow quickly. Doesn't matter. We should have basic concepts. Let's see, what should be a time complexity of an algorithm which has two loops inside? Where is the okay mark here? For example, I have a loop which runs n number of times, but then I have another loop inside which runs n number of times. Again, if I do n minus 2, n minus 10, it doesn't matter. Okay, this constant number doesn't matter. We care about this n. Okay, so this loop runs n number of times, this loop runs n minus 10, which means a little bit lower than n. So okay, both are n. Okay, so this is how we compute time complexity. Then we have some code here, but no loop. So rest of the operations are constant. We have to compute time complexity using this. So whenever you have one loop inside of another loop, and they are dependent on your problem size, just like this, n and n. So time complexity will grow like this, big O of n square. Why? Any clue why it is big O of n square? Because if your outer loops run 10 times, or no, 2 times, and your inner loop runs 10 times, how many times this loop will run? until it reaches to this point, end of your code. How many times? It will run 20 times. One time it will run and 10 times it will run. It will run again and 10 times it will run again. So total 20. So 2 times 10 is 20. So n time n is n square. So which means this loop will run maximum n square. This loop will run maximum n square. So n square is the worst possible time taken by algorithm, or in other words, big O of n square is time complexity of this code, which has 2 nested loops. If I add another loop inside, another nested, that runs again, for example, n minus 20. 20 is constant, forget about that. But it means now for every loop, I have another loop. And for this loop, again, I have another loop. So time complexity will become like this, and raised to power 3. Time complexity will become big O of n3. Which is a bigger number. This is not linear. So this is how we compute time complexity of algorithms, by looking at the algorithm, how many loops your code has, and by checking the general number, how many times the loop will run, it will tell you the algorithm complexity. Yeah, so let's discuss about this. Logarithmic is a lower number than big O of n. Big O of n means n times. So log of n is a smaller number. Okay. So for example, I give you an example here. Let's refresh that. Let's, wind this topic up. Big O of n is a linear operation or linear functionality. Big O of log n. This is logarithmic function. And this value, log of n, is always less than that particular n. So if your method performs log n, it means that is better than an algorithm which performs big O of n. Because this value is smaller, log n is smaller than n. So sometimes a method works like for big O of n times. However, we have similar method working in big O of log n times. So use big O of log n then, because that is efficient. So they're talking about logarithmic functions, which is like log of number, log of problem size number, polynomial time algorithm, for example, n raised to power 2, 3, n raised to power 10. And then they talk about exponential. An order of complexity that is worse than polynomial is called exponential. An example rate of growth for this order is 2n, 2 raised to power n. So they have designed all these methods here. N is linear, n square is taking more time, more operations, so n square is higher. Log of n is lower than n. This is what we discussed. Log n takes less time, so this is lower. Then n square, then n cube, and then 2 raised to power n, which is exponential, and exponential is the worst. This is a very big number depending on the problem size. So if we have 2 loops, we are right here. on n square. If we have single loop in our, code, we are on n. Now, you didn't ask me a question. Your code may have a loop like this, then another loop like this, but then after that they have another loop like this, separate. Then after some code they have another loop. So complexity of the code will depend on this again, because this loop separately will take big O of n. This loop will take big O of n, because this loop will run n times, this loop will run n times, this part will run n square times. So what is the highest value? Big O of n square. So which means mathematical value becomes big O of n plus big O of n plus big O of n square. This is one code. I mean, I'm talking about code. This is your one method, which has two loops like this. Then they have another loop. Then they have another loop for printing array, for example. But your complexity will depend on that part majorly, because this loop will run linear, this loop will run linear, only this will run more. So big O of n, big O of n, big O of n square should return big O of n square. So that's the mathematical part of computing time complexity. However, I will suggest look at the loop, the maximum nested loop, and compute the complexity. That's the easiest way. We don't need to check these separate loops because we already have two nested here. So we can check time complexity from here. The rest of the operations are constant time, which means big O of 1. And this is how we compute time complexity. Linear. Okay, so for big O, yeah, same notation we're talking about. Okay, so now anyone can tell me what is the time complexity of this algorithm? Whatever concept we covered so far. So let's see. They have a definition of a method, constant operation, a loop, and this loop will end where? Right here. This is the loop. Okay, and last return statement is a constant operation. So let's focus on the loop. How many times it runs? So it runs from 1 to length of the list. So length of the list is problem size. So this loop will run as many times as there are number of elements in the list. So that's why we have length of list. How many elements are in the list? This loop will run that many times. So this will tell the time complexity of algorithm. And time complexity will be big O of what? Anyone can tell me? Let's write it formally. We have learned that, right? The time complexity of that algorithm is, yeah, please.
Now I was saying, is it O to the n?
Sorry?
Is it O to the n because it's only running one loop?
Yes, it is a linear. This is just one loop. So it is a linear function, surely. But the exact time, how much time it is going to take, how can we write it, using that notation, big O of notation? You're right, because this is a one loop, okay? One loop, and one loop means this is a linear function. And linear function time complexity is big O of n. This is what we know. You are right, okay? There's something like that. But here what we have, we don't have n. Instead, we have list. So we can say length of list. So the loop complexity is big O of length of list. Because this number tells maximum, how many times this loop will run. And that will be the maximum time taken by the code. Rest of the operations are, quick. They are constant.
So is that how we write it? The big O length of list?
Yes. So this is the time complexity.
I see.
Yeah. big O of length of list. Which is the worst possible time taken by the algorithm. Wow, good. Let's see another algorithm. We have break time, but let's discuss another. Okay, very cool. Almost the same thing. We have constant operations, single line operations. We have single loop, while loop, which is based on length of list. And then constant operation, this constant operation. So this is the loop. So we have to see how many times this loop runs or return position. Okay, yeah. So this loop runs length of list. Again, complexity of this algorithm is big O of length of list. Length of list is actually representing n number of elements in the list. So this is linear algorithm, linear time algorithm. This time is taking linear time. Here somehow they're using big O notation for best, average, and worst. But whatever I discussed, that is like more formal from theoretical computer science. That's fine if they're discussing the same for simplicity. They're using same big O for average and, you know, for best and worst case, everything. We are not talking about best and worst, best and average. We're talking about worst. If we are sure about worst, somehow we can convince ourselves what can be the best complexity of an algorithm. Best means, just like I showed you, if you are finding an element in list and that occurs on the first. So that's the best case. So in this way, we find the best time. What is the minimum possible time taken by algorithm? So let's have another algorithm and then we take a break, okay? Show me some code. Selection sort, okay. All right, this is good. Definition, constant time operation. All right, so let's, yeah, well, that was the plan that we will discuss time complexity, which we did. Other than that, I would say, let's go through Canvas if we have some. Oh, no, not this. Deadlines for the final week is somehow a little bit different. If you guys have idea on that, I don't know. Let me just share, because attendance will be marked for the final week. We have different dates a little bit, because for example, this is week 5. You have to submit, yeah, by Tuesday. First post for to be present, first reply to be present on Wednesday, and then second reply to be present on Thursday. So Tuesday, Wednesday, and Thursday you are due with your, you know, with your post. Discussion post, main post, with the 2 replies on the consecutive days, Tuesday, Wednesday, and Thursday. You don't have any gap for the final week. If you submit your first reply, what is that? If you submit your first main post instead of Tuesday, if you submit that on Wednesday, it will be marked as tardy, and after Wednesday, it will be absent. And similarly, if you don't submit your first reply on Wednesday and submit that on Thursday, you will be marked as tardy, and after Thursday, it will be absent, okay? And for second reply, you have, you know, Thursday to be present. I don't see Friday here, because for Friday they haven't marked anything right here. Yeah, so no tardies for Thursday's post. This is one. This is important. So you cannot submit your second reply late. So the deadline is Thursday. So you should submit your second reply by Thursday to be marked as, present. After Thursday, it will be absent, no tardy, right? So this is for week 5. Okay, new dates. So yeah, let's go ahead. Let's see what else is here. So we are on a review hands-on exercise. I think this is one something needs some theoretical part from your side where you have what? Yeah, use of array and link structures, interface and polymorphism, inheritance, and abstract classes. Learn about stack and how to use stack. Complete 10 review questions under each chapter 4 to 7. So this is what your main work or task is, exercises. So you have to cover your chapter 4 to 7 and 10, I mean, there are review questions, so you have to complete 10 review questions for each chapter. So this is the major thing, I believe, for this week. Hands-on exercise. What else you have? The discussion post, again, it is about UML. I have to post on that part as well. I will post it today and you guys can proceed, you can submit your discussion post as well. In assignments part, we don't have much here, just one part. So let's see this. And then the quiz, week 5 chapter quiz. That's it. Yeah, that will end the course, and assessment will be done, which is your final exam, and that is due by Thursday till 12 p.m. Yeah, your final exam or assessment. So this is your chapter. Let's see the review questions. For example, this is your chapter number 4. So you have to cover 4 to 7. So basically you will be covering major data structures, array, link structures, then stack. We worked on stack as well. So for each chapter you have to do that. So let's see, where are the review questions? I mean, this chapter 4 is really, detailed on the linked list types, single linked list, double linked list, and then circular linked list. Everything is all around linked list, and they have so many, diagrams because they are discussing everything in, through proper, visualization. They are also discussing about the complexity, time complexity of methods. So I believe now you should be able to see the time complexity by looking into the code, how many loops the code has, and what should be the time complexity, okay? But again, if you have questions, do let me know. Let me see, okay, so this is summary and this is review questions, okay? So for every chapter, you have these review questions. So these are just 10, okay? So maybe you have more, I don't know, for some chapters, but you have to review these questions and you have to answer accordingly. So this is the task, to submit the answers for review, okay? Let's go ahead and do that part. Assignment, complete code with stack. So we have worked on the stack code. Complete the started code and utilize code commands to follow along the design logic, okay? After completing, incorporate it together with reverse word. Okay, so they have another file in which we can download from, from here in the files. Open up. I don't see it. Starter code, week 5. So we download this file, and what they want is they want us to use that, to use this file and add stack there. This is what they have written in the description. So let's download it and go back and see what else we have to do. So I am downloading this from student files. Open, yes, open. Where is my Visual Studio Code? Do I have it here? Open file. Downloads. Reverse word to do. Okay, yeah. So this code we have to use for completing the task. Let's see which task it is. I believe they want us to use stack for reversing the word. And we have done similar example in last week. So I think this should be a short, small code to implement. Yeah, complete code with stack. So we have stack already implemented. So we have to complete the code which I downloaded to follow along the design logic. So use stack.python file and add it into your reverse word py.code that calls functionality from stack. Okay, that's it. So we have this. We have this file here. I have opened it 2 times. I don't know. Okay, so reversing a word. So we need to reverse a word using a stack. This is the task. For this example of using stack, examining a simple stack, reversing a word. When you run the program, you type a word, and the program displays the reversed version. This is the task we have to complete. Okay. I think last time we did an example which resembles the same thing. We were working on palindrome, right? For palindrome, we divided the word, we pushed the half part on stack, and then we popped and mashed with the remaining half if the characters are same. This is what we did for palindrome. For reversing a string, that's really simple, I would say, because whatever we push on stack, whenever we pop, it is already reversed. So what should we do? We should push in stack and then we should pop. That's it. Because whenever we pop, it is reversed already. So this is really simple. Let's see the comments. Create a stack to hold letters. Okay, let's make a stack here. Import stack. I'm just deleting all this. Import stack, which file it is, which contains the code. Stack to do or stack, something like that we are using in our previous codes. Stack to do, okay. So I have my stack implementation in this from stack to do, import everything. Oh no, from stack to do. All right, so we imported, we added our stack code, and now we need to work on that, which should be simple. So let's create a stack.
So that's the stack to do from last week?
Yes.
Okay.
The same stack. Yeah, we just need to apply it for reversing a word.
Okay.
Yeah. So stack is create a stack of some, some size, for example, 100. Get user input. Let's take an input from user. Word equals input. We can ask user to enter. Enter word to reverse. That's it. So we have to take user input and after that loop over letters in word and push letters on stack if it is not full. Yes, we have to check if the stack is not full, and then we should keep pushing the letters there. So for letter in word, for all the letters, right? We have to push everything. If not, stack dot is full. If it is not full, only then we can push, right? So stack dot push or not peak. Push letter. Okay, so for every letter in the word, we will push that on stack. Whenever we pop, it will be reversed. So we have to print that after popping. Yeah. Build the reversed variant. Print. Okay, build the reverse variant we have to do here. So which means while stack is not empty, we have to, pop it. Stack dot is empty. While not is empty, stack dot pop. Okay. It will pop and it will return us, something. So we have to make a, reverse string, okay? Because popping will be single character. So we have to make a string. For example, let's make it here. Reverse word equals, initially it is empty. So we can put the data here, reverse word, and keep on adding whatever we pop from stack. Actually, popping should be done right here. So whenever we pop, we put it in reverse word so that we create the reverse word as well. And then we just need to print the reverse word. Print reverse word. So it should print the reverse. Yeah. Reverse word is. That makes it better. So we pushed all letters and then we popped all letters and then we printed the reverse word. That's it. Enter word to reverse. So we have to enter something here. We have to input something. For example, I enter week 5 Python. So it is returning the reverse. If I run it again, I enter ABC. Oh, not here. I enter ABC, so I get CBA. Reverse word is CBA. So it is running fine. That was a small application for stack, for reversing. Okay. So you see that it is taking characters. So basically word, you can put sentences as well. Because, everything is a character. If you put space, that should be handled as well. So you can put a, complete sentence instead of a word. Okay. It should work. Because space is a character as well. Space is also a letter, just like a empty letter. Okay. So any questions in that? We used whatever we have built in already from stack. We took input and then what we did, just a push loop and a pop loop. Yeah. That's it. That's all they need in the application in this assignment. And the good thing is what you can do if, let's add the palindrome part. If word is equal to reverse word, it means word is a palindrome, right? We can check both now. Word is a, because we are also reversing. Else, not palindrome. That is not required. I'm just, checking, because we have our complete word and we have the reverse variant. So we can check if both are same, it means it is a palindrome. If both are different, so then it is not a palindrome. So for example, let's enter a palindrome string. Palindrome string, let's make it PALA. Yeah, so it is a palindrome string because it is read same way from backward and forward, right? From both sides. So the reverse word is same thing, so that's why word is a palindrome. Yeah. So any questions in that? Well, that's all for today, I would say, because this part is, we have discussed it, how to do that. Other than that, you have to, do the review questions and then discussion. And of course, your final exam is due. So yeah, that's all for today. Now, I mean, we can discuss whatever your questions are if you want to ask anything. So I am here for next, 2 hours. Kiara, you were having some questions. We can discuss that now. And I wish you good luck for your final exam and assessment. Yeah.
Do we still
Thank
have
you,
class
Professor.
tomorrow? Oh, sorry.
Sorry, I'm sorry.
No, you're good.
Thank you, Professor. Good night, everyone.
Good night.
Good night.
You too, Thomas. Do we still have class tomorrow?
Sorry?
Do we still have class tomorrow?
No, we don't have class tomorrow. Oh, sorry. Yes, tomorrow, actually, I will be online. Just in case if someone has any questions regarding, exams or anything. So I will be online here for that part. But we have covered most of the stuff. If someone has any questions regarding coding, anything, so I will be here for 5 hours for the whole time of class.
Okay.
So my concern will be if someone joins or not, but my plan is that I will cover some of the, arrays and, bags applications a little bit, just like we did for chapter number, for the time complexity chapters. So I would like to do the same thing, a little bit of revision for further chapters, but we will not be discussing anything from Canvas because Canvas is done. They don't have anything from there. I will discuss a couple of codes from my side. Yeah.
Okay.
Yeah, that's the plan. Do you have any questions?
What you were explaining earlier with the big N and stuff, made a little bit more sense. I'm kind of tired too, so I'm just like kind of like in and out. But yeah, I don't really have any more questions for today. I'll just join class tomorrow if I have any more questions.
Oh yeah, sure. We will
Yeah.
discuss that tomorrow. See you tomorrow then. Take care.
Thank you. Take care.
Bye.
both the array bag.
Uh-huh.
This is not the right array bag. Is this it? Oh, it's over here. This one and arrays. Okay. And test bag one. Okay, these are my three files I'm working with on this project. And the test bag, you know, I haven't touched anything in here. This is to test, except for I put this stopper in there. That's all. We don't need that. Okay. And and the array bag, I have the formula for the remove, right? The function, the method.
Yes.
Is just like target index
Yes.
equals 0, and you know it breaks if it finds it. If not, or if it finds it, then it increments the target index.
Yes.
So what's happening is on my output, I'm getting expected 80, right? As in the I believe the test bag. Is it test bag has expected 80 and length of the array should have been 80. I'm not getting that. And when I check it and I take the new or the temporary array, right, before it copies everything over, and I'm gonna run it, and let's see what we got. So I run it, and as you can see, 80 is the length of the array is 40, but it should be 80. So if I go in and let's just say I'm testing this and I change it here, right? That should give me, if that's twice as much, that should give me 80. Let's see. And it gives me 160.
Okay. Right. So you are getting trouble in the array or array bag itself?
So the length of the array is what I'm trying to get the right length of the array, and it's not somewhere something's wrong because the computer's going to respond to whatever I put in. So I'm thinking, I thought it was in the formula here, right? The loop, but it's not.
Okay, yes. If you can you share me the code file so that I can open
Yes,
it on my side?
absolutely. You want all the files or just the array bag?
I would say array bag.
Okay.
No, not exactly. I believe that in array bag we are using um, array as well, right?
Yes.
And I will be needing, I believe, array class, whatever class you are using, and array bag both.
Okay. All right. So, oh man, that's not what I'm trying to do. See array bag.
I don't think so that in class we got some issue like this, but I can open my file as well meanwhile so that we can,
Okay.
see it quick.
Yes. Okay. Uh, and the test bag. Well, test. Okay. Let's see. Drop file here. Drop.
I would say I need your test bag and array bag because these are the core. Arrays, basic. Array bag and test bag.
Okay. I just sent them over, Professor.
Yeah, I got it. Let me just test bag 1, array bag. Let me just download it and then go from there. I download it and then I share the screen so that you can see it.
Okay, sounds good.
Sometimes the issue is really minor, but we are stuck, Okay, so it needs one more file array. What I'm doing, I'm just using my arrays so that your code runs, because arrays file should be same we used in the class. So
Right.
let me just
Yes.
share the screen because I got your code. Okay, yeah, so code is running on my side. One moment, let me just see the desired output. Okay, so let me share the screen. It's working on my side, and let's find the error. Okay, so there I am. This is your code, which I have opened right here over here. And I have run the test code. Somehow we see the, issue here, expect 80 as length of array equals 80, right? It should be like 80.
Right.
Let me just see, 1 to 11. These were the pre-written methods, so there should not be any issue in this file because that file was already available to us to use. So so we are using test resize here, and so before test resize, we should make a edit 100 items, length of back is 100. We should call this test as well, I would say, for our test for our array bag, because we did the work for two classes, for linked bag and test bag. So in test, for before resizing, we were running the test method as well for array bag. So, and array bag class, I believe you also imported that because we have this array bag right here. So you have already over here. Yeah. So you have that array bag. So basically what we need to test, we are testing this array bag. So let me just add this because this class is existing here. Okay, so from arrays import array could not be resolved. But I added that on the same place. Let me just have a look. Yeah. Array. Where is array? Test bag, array bag. Oh, I don't have array here. Okay. Where did I copy? It need one more file for array, right? So oh yeah, array is there. It is there. So it is using the arrays file, whatever file you are using. So we are on the same path. So let me just run the code. Expect 80. Remove remaining length of bag is 0. Expect 10 as length of arrays. Okay, so now the output should be, the error is somehow here, which you said, length. So let's see the length method because this test bag is totally fine. We didn't change anything here. in array bag, if I go to where into my length is returning the number of items in self. We are returning the physical size because there are two sizes. One is physical and the other is logical. So
Right.
let me just know how many number of items are there we return. So string, let me have a quick look and see. Add equal. Okay, so here you are adding and we are doubling it, which is okay. Yeah, that's fine because this is what we did in class. I doubled the size. There was no requirement, so I doubled it. Yeah, that is the same thing. I doubled. Yeah. And for removing, if length of self less than equal to self dot items divided by 2 and 2 times length of self array bag. Yeah, this looks quite okay because I had the same condition. Length of self less than. Okay, so I found a difference.
Oh, I see.
And 2 times length of self greater than equal to. Let me just see how it is. Let me just see the output and then we discuss. That is one part of it. It is not affecting, because that was a remove method. It's up to us if we decrease into half or if we decrease to 1/4, whatever. So this is just condition how much we want to decrease. So it can be by 2, by 4, by 8, anything. So that's why we don't see any difference right here. And here output is, yeah, so the output should be like that. Removed 76, that it says removed. Yeah. And then length of array is expect 80 as length of array.
So the length of bag dot items, that would be the length of the physical array, right?
Yes, how many items are there? Exactly. I mean, because you didn't change anything in the file so far, it doesn't look like that something is. Expects 80 as a length of removed, expect 80 as length of array. And then it print length of bag dot items, but then bag, because it removed, so bag size should change. So it should be 80 right here at this point. So basically we are accessing bag items. So let's see the constructor. Capacity is 10. Yeah, this is what I have. I started with 10. And then we have size, self.add item. Do your arrays, array class is the same which we used, right? So can you check your array? It returns self.items. It should
Okay.
be.
Let me see. Just okay.
Yeah, just the length.
The length, yeah, returns length self.items.
Self.items, okay.
Yes.
Okay, so can you check your array? Does it has this line? Because one line was missing in the code in class.
No, it doesn't.
It doesn't have it.
Class array object. Let's see.
Can you check?
Items. Yeah, it has self.items. Yes.
You have it?
Yes.
Ah, okay. Because this one was missing somehow and the code was not working in class and we fixed it out. So you already have it.
Mhm.
And then, then it should be there. Really? Self dot. What should I do? You are using same file. Nothing is changed. Let me just edit 100 items. Okay. Removed. So somehow when it says expect 80, so at that point we see error. Let me just put a breakpoint and see what is happening. That may help. Run, start debugging. It goes of 11. So it means it is not removing, right?
Right. Right.
Maybe because whenever we try to remove, here we are adding, it is added, but when we removed, actually removed 76 items, expect 24, so it is 24. But why length bag dot items is not okay? Let me quickly do one thing because
Okay.
we want to make it run somehow. So stop debugging and test bag, array bag. What I will do, I will just, because somehow it looks something is, kind of, I will undo it, but let me just do it once to see where is the error.
Okay.
Which part works. So just trying to, copy paste it. Now it is okay. Yeah. You see, the issue is somehow in remove method.
Mhm.
You see the output is, now it is working. So maybe some again, one minor thing is missing. So let me just do it, undo it and then try to find issue in the array bag remove method. Maybe again, some issue which we always find, indentation issue. We always
Right.
find. I don't know. Let's see. Because the issue is only in the remove method. This is what we saw. So I will exactly match it with my method. I mean, it should be same, but still let's try. There should be really very, very minor thing. Okay. So when I remove target index for target in self, target equals item break, try and range target index to length of self -1. Okay. Range, it looks exactly the same thing,
Mhm. Yes.
exactly the same thing. Okay, so this part is comment and I am just comment. I mean, it should, does it change something?
Mhm.
If item not in self, in that case, just say it is not there, right? This is just exception, an extra part, but it should not accept, it should not affect the output. So, yeah. So, is it exactly the same line? Because I checked it 2-3 times, it looks same. If I, and 2 times length of self greater than equal to. Okay, just put a line. Whenever we put it on next line, we have to use this sign.
Mhm.
Okay, found it. Whenever we
Mhm.
are making new array, whenever we are making new array, which is temp for new size, decreasing the size, we have to
Right.
reduce the size.
Right.
But here we are making, what the code is doing, we are making the same size, whatever the, data is, that even after removing the, whatever items were removed, they were there in the size. They were show
Right.
that items. So we have to divide it,
Okay.
divide by 2. I mean, you can do divide by 2, or, you can divide it by 4. It will be very small. It's up to you, whatever you want to do. So there is no specific restriction, but size will decrease only when we will do half. So that new array will be half size. So right
Okay.
now it shows us, more, but now if I go back and run it, it should show the 80 as length of 80 and 10 as length of 10. So only one thing, a small bug, that you should make new array with smaller size.
Okay. I see.
Rest of the stuff is okay.
Okay. With this, would you want to, depending on like the rate of growth of your array, would you want to set up different conditions for that?
Sorry?
Like for your rate, based on your rate of growth for your array?
Yeah.
Like, maybe let's just say in the first hour you got like 700 participants, right?
Right.
You would want to double that for the next hour, or would you want to look at that and based on that hour, like quadruple it?
Yeah, so actually it depends, because in assignment there was no restriction. So what we are checking, we check if physical size equals logical, which means the length is full. So what we do, we make the size double. You
Okay.
can make it 4 times, you can make it 3 times, it's up to you. So what I did, I
Okay.
just doubled it, because double is good enough to put more data in. But in assignment, there was no restriction. So either we grow or we decrease. It's up to us how much we want to do.
Got it.